All right, let's continue on with section 7 here with allylic halogenation. Now, we do know that the weakest CH bond, the one with the lowest bond dissociation energy, will undergo radical hydrogen abstraction faster than others. We saw that with the bromination selectivity. And we do know that from our very beginning discussion here that the CH bond that is in an allylic position would be the lowest bond association energy. That's what we see here at the 364 kilojoules per mole. Now, the reason for that position having the weakest bond is because the radical that is resulted from that homolytic cleavage of the CH bond would have resonance and stability. So we are going to see that there are very specific reactions that alkenes can undergo with hydrogen abstraction at the allylic carbon. Now, that hydrogen abstraction at the allylic carbon, we said it has resonance stability. So let's just review that resonance structure over on the right-hand side. Remember, one arrow at a time. The radical will go and share with another electron from the pi bond. The second electron from the pi bond is going to become a radical on the top left. Let's just label these 1, 2, and 3 for the carbon so that we can see the rearrangement there, the resonance stabilizing effect. So when we think about that allylic position, we can do bromination of that allylic position, but there's a problem. The main problem with using Br2 with heat or light at the allylic position is that we actually get another product. Let's go ahead and take a look at that product. We actually get addition, right? Yes, we are using a radical initiator of heat or light. Here is written with light, but we have competition. Because there is so much Br2 in the solution, we can't make that homolytic cleavage happen for every single bromine diatomic. So we get these two different competing products. And so typically we do not like to use Br2 when we have an allylic position being brominated. Instead, what we want to use is a bromine source that keeps the amount of bromine low. So we will use NBS, N-bromosuccinimide. Notice it's one equivalent of bromine radical for every one molecule instead of Br2, which would have been 2 equivalents of bromine radical. The initiation step here for this reaction starts with the homolytic cleavage of NBS. So NBS instead of Br2 will be over the reaction arrow. We still should use heat or light. Here we have light written. So what would happen is a homolytic cleavage of that NBr bond. Notice we have a nitrogen radical and a bromine radical. The nitrogen radical is relatively unreactive here. It will not be doing any of the hydrogen abstractions because it is more stabilized. Why? There's resonance there. If we want to imagine what that resonance looks like, one of the pi bonds from the carbonyl can do resonance with that nitrogen radical. Showing this resonance just for our own purposes to be able to see how stable that nitrogen is. And so Br radical will continue on in our propagation steps. So just again to confirm, we use NBS over the reaction arrow instead of Br2 because NBS will keep the amount of bromine radical and Br2 low so that we don't have any competition with reacting the pi bond in the alkene, like what we saw in chapter 8. Now for our hydrogen abstraction and halogen abstraction in this reaction, we will see two propagation steps. The first one will be of the bromine radical coming to make a new bond with the hydrogen. Hydrogen abstraction, we're pulling off the hydrogen. The other electron in that bond will go to become a radical on the carbon. Now this is very similar to what we saw previously with our halogenation reaction. It should be very similar. The only difference is the first step when we do homolytic cleavage of NBS. Second step, we do see Br here, Br2, and I'm going to explain why. You could also use NBS to do the halogen abstraction in the second propagation step. We're going to use Br2 right now just so that we keep things a little bit simpler. This would add that bromine onto our organic molecule at the allylic position. Now the termination step is how I'm going to prove that we do have some Br2 in the solution. Remember, a termination step needs to be shown just to say that we've ended this reaction. However, it can be involving any two radicals that we want. Just to show you that we do have some bromine diatomic in the solution, I'm going to show you that there is a possibility of a termination step involving two bromine radicals to become Br2. So that's why we do see that Br2 can be used in the propagation step. You could also use NBS. It's just a little bit more complicated to draw. So feel free to use either one in the halogen abstraction propagation step. And again, any termination step can be drawn. I'm choosing the simplest ones to draw to keep things a little bit more light. Allylic halogenation with NBS sometimes produces multiple constitutional isomer products. Now, when that happens, how do we know? It's when we see an allylic position and the alkene is asymmetric, right? There's no symmetry in this original alkene. And so when we see the product, we know that this is the most stable allylic position. However, when we imagine that that first radical is formed from the hydrogen abstraction, we know that there is resonance stabilizing that allylic position. And so what we have to be able to draw is both radicals to show the multiple products that could be formed. All right, so we do have this blue radical going forward in halogen abstraction to make the first product. We could also see this green radical going forward to make the primary in the bromine or the halogen abstraction. All right, now when we are looking at that delocalization, halogenation will occur at either site regardless of stability. We will have multiple constitutional isomer products in this reaction. So we do have to take into account all intermediates. Radical addition of HBr. We saw this in chapter 9. We're going to now do the mechanism in chapter 10. I held off doing the mechanism at first because I wanted to make sure we had a very good foundation in radicals before getting to this mechanism. Now, this is an anti-Markovnikov regioselectivity. That does not mean that when we throw in a peroxide that we are going to see a carbocation appear on the less substituted center. It does not mean that we are going to see a radical appear on the less substituted center. With peroxides, anti-Markovnikov addition occurs because we are doing a radical mechanism. And so it's a different mechanism, and the actual addition of things, H and Br, are opposite of each other. And so let's dive into this mechanism. The first one, the Markovnikov addition from chapter 8, did heterolytic cleavage, where we made a carbocation on the more substituted position, and then a bromine nucleophile will come in on that more substituted position and make the Markovnikov addition product. With a peroxide, we still are going to be adding hydrogen and bromine across that double bond, doing an addition reaction. However, it's going to be via a radical mechanism. Let's dive into the initiation. The reaction is initiated by thermal homolysis, which is just going to be the peroxide originally splitting homolytically. We'll see that peroxide bond is going to break 1 electron on each side. Just in case I haven't mentioned, the arrow for that peroxide can either be on the top or on the bottom, right? So it doesn't matter where you start drawing your arrows. Either way is a-okay. But what this makes is it makes 2 peroxide radicals. And this is what's going to be going forward in our initiation step. Notice that the second step doesn't look like an actual initiation. The reason why it's hydrogen abstraction is encompassed here in the initiation is because we're waiting for the bromine radical, the radical production that will actually continue on with the organic molecule. So we're still doing a little bit of prep work here in this second step. Also, if you look over on the right-hand side, we can see that that first reaction requires heat because the enthalpy is unfavorable, right? It's endothermic for this first alkoxy radical production. So it's really that second step that is exothermic that helps us initiate this reaction fully. The peroxide radical will come pick up a hydrogen and it will make that bromine radical to carry forward. Notice here that we are going to be making a bromine radical. Never in our reactions will we ever see a hydrogen radical form. So in order to do this reaction, we are aiming in the initiation step to prepare the bromine radical itself. We'll carry that on into the propagation. Now in the propagation step, let's think about where do we want the radical? We are going to be putting bromine first onto our alkene. Notice that this is the opposite of what we did in chapter 8 with our heterolytic cleavage. Homolytic radical reaction is still generating the more stable radical. We are simply just adding bromine first. So when that bromine radical goes to add onto the pi bond, we still will make the more substituted carbon gain the radical, similar to how we saw the carbocation being put on the more substituted center. Notice that radical is on the more stable side, the more substituted side. Bromine gets added to the less substituted side. If you thought about switching it, putting bromine in this step on the more substituted side, you would actually get a much less stable radical. This is not formed. Wanted to draw it just so that you could see that secondary radical and debate with yourself. Do you want the tertiary carbon radical or the secondary carbon radical? Always choose the more stable. That's the one that's favored. Now the second step is a hydrogen abstraction. So we have an addition to the pi bond where we add the bromine, and then we will take HBr and do a hydrogen abstraction. That's going to put the hydrogen on the more substituted side where the carbon radical was. And the propagation chain will continue with more bromine radical. Let's just show a termination step, that coupling reaction of the halogens. Again, any 2 radicals that you see will constitute a termination step. The only radical that we have not seen, and I never want you to draw, is a hydrogen radical. very unstable, most likely never going to form. So don't do it. You can take 2 carbon radicals, you can take a carbon and a bromine radical, you can take 2 bromine radicals. You can even take 2 of our epoxide radicals. To remake the peroxide. But don't ever take a hydrogen radical in any of these steps. All right, just a little bit of understanding again when a new chiral center forms. What we want to be able to say here is that when we form a chiral center, right? Notice how carbon 1, carbon 2, carbon 1 is now chiral. Just like before, any of our radical intermediates, any of our alkenes will be considered sp2 hybridized, trigonal, planar, having a top and a bottom side. And so therefore, we do understand that this would be a racemic mixture. Notice carbon 1 is chiral, carbon number 2 is not. I do not need to show stereochemistry if I don't have a stereo center. And so therefore, we would just see these 2 products. Now for a little bit of extra fun with some real life radical chemistry. I wanted to go through a couple of real life reactions that are in your textbook. These are actual sections and the section number will be written up at the top. We'll start with section 8. Now in these sections, I won't be directly asking you for questions on these, but I find them fascinating real life applications that I feel are very important and an important aspect of this chapter. Ozone, O3, is in our atmosphere. We've heard a lot about climate change, that ozone is being depleted, and ozone is an important aspect for our environment. Why? Well, because ozone is both created and destroyed in the upper atmosphere via a radical mechanism. O3 can actually decompose into oxygen gas, O2, and oxygen radical. Woohoo, a radical. Nice. When that happens, or why that happens, is because the UV radiation from the sun is being converted or utilized in this radical decomposition. That oxygen molecule and the oxygen radical then reform to form ozone, and they combine and release heat. And so heat comes into our Earth, not the UV radiation. Ozone is an important aspect in our life. Heat is a more disordered form of energy compared to light, and so that's why it's helpful for us. UV light is a little more concentrated, and it actually can damage our skin and damage our biological processes. So we need ozone to be able to convert this energy of light from the sun into heat to warm our Earth and to warm us. This process is spontaneous because of the increase of entropy. However, ozone depletion is a serious health and environmental problem. Without ozone, the UV radiation would penetrate our atmosphere and wreak havoc on everything. One of the main contributors that is believed to be a culprit is the use of chlorofluorocarbons, CFCs. Now you can find these most often if you ever have seen aerosol cans, whether that's hairspray or paint spray bottles. These molecules, Freon, even these ones that are shown, these will reach the upper atmosphere. They're very light molecules, and so they will reach the upper atmosphere and react with the UV light to form chlorine radicals, just like what we were talking about. There is an initiation step once it reaches that upper atmosphere where there's enough UV light, and it will make a chlorine radical. Now, why is that bad? Because that chlorine radical will then go to react with ozone in a propagation step. This is very, very bad because then we make O2 and there's no ability for that oxygen molecule to react again with the oxygen radical to reform ozone. So there's no continuous process of formation of ozone. It's depleted and that's it. Chlorine radicals are formed in this step, and then the destruction of the ozone molecules will continue. CFCs have been replaced with other alternatives. These are not as harmful because they don't have chlorine, right? A chlorine radical is not produced. And so therefore they are not as harmful for the depletion of the ozone layer, but they still are acting as greenhouse gases. That's a different subject for another day. Auto-oxidation is a really interesting process. It's when atmospheric oxygen can form a hydroperoxide. So it's this carbon, oxygen, oxygen, hydrogen functional group. This process is usually generally really, really slow. However, it is formed with a radical reaction. Now, you don't need to know this radical reaction, but why is it important? Well, when we start thinking of these radical reactions happening, we actually see that formation of our hydroperoxide is actually one of the problems with explosives for ethers. In the lab, we use diethyl ether quite a bit in organic research. And so it actually has to be stored at a very, very specific temperature in a very, very specific canister because of the auto-oxidation that could happen. Hydroperoxides can be very explosive. And so we have to store ethers very carefully so that we don't lead to lab accidents. Also, another one is antioxidants. Triglycerides are really important to a healthy diet, but they're also susceptible to auto-oxidation, specifically the allylic carbons, because we know that allylic position, right next door to a pi bond, is the most stable radical. Auto-oxidation occurs here, and that's how food can become rancid and go bad. And so triglycerides need have a shorter shelf life unless they are preserved, right? Preservatives can also be called radical inhibitors. Now, these preservatives are used primarily to prevent the auto-oxidation reaction. How? Because they themselves can actually undergo the radical reactions instead of the fatty acid chain. So BHT can undergo a hydrogen abstraction to scavenge the radical that would otherwise initiate auto-oxidation. And so that's why we often call these preservatives antioxidants, because they are preventing the auto-oxidation that normally happens with molecules when it's exposed to air. Natural antioxidants, such as vitamin E or vitamin C, can find their way into our biological systems and be radical scavengers. So they can undergo hydrogen abstraction. Notice that when things are hydrogen abstracted, that there is more resonance in these specific positions. And so that's why they are more favorable to undergo that auto-oxidation or that radical mechanism instead of the typical fatty acid chain. Last one that we just want to talk about is polymerization. When we make multiple chains, this polymerization process joins together very small units. These units are usually called monomers, and they usually have an alkene with them. Now that alkene is initiated into an addition reaction, a radical addition reaction, and that radical addition reaction can cascade and make more and more connections. Now a polymer usually has the subscript here N for its unit to say many, many, many connections followed. This type of idea for polymerization is really one of the ways that we make very strong glues and also very strong plastics. Now again, radical polymerization usually proceeds via a radical chain mechanism with that peroxide, and then the peroxide is used to do an addition reaction, very similar to what we see in the radical addition of HBr. But here's where the fun part happens. Once one addition unit happened, what we saw previously on the screen, a second can occur. So you have 1 unit and 2 units, and then a third can occur, 1, 2, 3, a fourth, and so on and so on. And that propagation continues to go and go and go, giving you that overall net reaction. Now there will be eventually a coupling reaction that destroys 2 radicals, right? But it could be either between the other peroxide, or it could even be combining 2 chains, right? So we have a bunch of carbon chains bound together, and yes, chain branching can occur. You can think that this polymerization, this radical mechanism, is going to just cascade and continue to add. Now, highly branched polyethylene forms give us flexible plastics. So if you start having multiple branching, the molecule itself, the polymer, is a little bit more flexible. The unbranched polyethylene is more brittle, like the top of the plastic container, right? So you can kind of see the 2 different styles or 2 different feels of the polymer, the plastic itself, and it's based off of what the structure of the polymerization actually looks like. Just to present some of the real life applications, propylene or 1 propene, 3 carbons with an alkene. That monomer can be used to make a polymer that is used in carpet fibers or appliances, car tires too. Styrene, it's the carbon-carbon double bond with a phenyl or a benzene ring attached to it. Polystyrene is used for styrofoam, televisions, radios, all sorts of things. The ones that are maybe a little bit more in the forefront of your life, PVC pipes, CDs, garden hoses, all of those use vinyl chloride. And then tetrafluoroethylene, with all those 4 fluorines on there, that polymerization reaction makes Teflon for nonstick coating for fry pans. That's all I have for our real life applications. I hope that can kind of bridge the gap between where do we use these radical reactions in real life, and give you some aspects of radical mechanisms happening in your own home.